with you all. Thanks for coming along tonight. My name is Dave Gregory. I am a Baptist minister. I serve in a church in Croxley Green, which nobody knows where it is. So it's just between Watford and Rickmansworth. Well, Colin will know where the Croxley Green is, probably. And I've been here for about, this summer it'll be 11 years as minister here. I used to be, I'm a physicist by initial training as well. So it's nice to have another physicist on the call, although they're still here. Yeah, there. And I spent quite a lot of time working at the Met Office in the European Weather Centre doing weather forecasting, developing weather forecasting models and climate models, which is where some of my interest in the environment and climate comes of what's called the John Ray Initiative, which is an environmental Christian charity and education charity trying to explain to people what is happening around issues of the environment and climate. And recently I've been part of a group which has started the Baptist Union Environment Network, which is a growing network amongst the Baptists together, churches in this country in different regions. So tonight we're going to be talking we're going to be talking about what's called the greenhouse effect. And one of the things I like about what Simon's done with this is not only is he looking at theology when he's thinking about environmental and climate issues, he wants to try and engage with the science. Now, it's often difficult to know how to pitch science because I don't know what exactly your science background is. So I apologize if A, this is too complicated, and B, this is too simple. I tend to aim, when I do these kind of talks, I tend to aim my science at kind of secondary school, kind of less technical level. So that's where we're going to go. So hopefully you'll be able to understand something of what I'm talking about. I'm going to share my screen because I've got some PowerPoint slides to share with you. Let's see if this works. Is that working? Okay.
Yes, but it looks small.
Yeah, that's because I need to do this. Is that better? Great. So as I said, we're going to be talking about the greenhouse effect. And I guess we're going to be talking about air tonight because the greenhouse effect is all about air. And so when I did my PhD research at Imperial College on thunderstorms, and I put a biblical quote at the start of my thesis. I put a couple actually: Jesus calming the storm, which seemed appropriate, and one from Job. Turned out my examiner was a Christian who worked at the Met Office, so it went down quite well, and I passed. So the quote from Job was from 38, and I'll share a part of it with you tonight. God speaks to Job in this part of the letter. Where were you when I laid the earth's foundations? Tell me if you understand. When I made the clouds its garment, who cuts the channel for torrents of rain and a path for the thunderstorm? Who has wisdom to count the clouds? Who water jars of the heavens? It was those last two phrases, dedication of my dissertation. I had a little smile on my face when I did that because there was one point in my research in those 3 years when I was counting clouds to do some research. Recently on the BBC, there's been a programme with David Attenborough, which I haven't seen all of. I've only seen some of it, called The Perfect Planet. Hang on, why isn't that working? Let's try this. Okay. It's frozen, so I'm just going to relaunch that. Right, so yeah, the BBC have been showing this series called The Perfect Planet, trying to explore why our life is so perfect for life. I wonder why you think that might be. I wonder why you might think this is a perfect planet. This might be a moment when you might want to unmute if you want to make a comment about that, or a suggestion about why this is a perfect planet. Anybody got any suggestions? Why is the Earth a perfect planet?
Because if it wasn't, we wouldn't be here.
Well, that answer. Well done. Any other suggestions?
Is it to do with the distance from the sun and therefore the temperature of the Earth?
Okay, so the distance from the sun, the amount of energy that the Earth receives. Okay, that's great. Any other thoughts?
God made it that way deliberately.
God made it that way deliberately? Yeah, that's the theological answer.
Is it because everything is linked together?
Yeah, that's one of the things we're learning about life on Earth. Everything is very connected together and relates to that. Yeah, that's human. Yeah.
There's something to do with us having an atmosphere, which means that the harmful stuff doesn't get in and the good stuff stays in. I think I was watching something to do with Mars used to have that and doesn't anymore, and therefore.
Yeah.
That's the complete limit of my understanding.
Okay, so something about the atmosphere protects the Earth from the environment that it exists in the solar system. So we've got distance from the sun, things are connected together. That makes it more robust. The atmosphere protects us from harmful things that might come from outside. You know, God made it. And any other thoughts about why this is a perfect planet? Yeah.
The Earth wobbling on its axis.
Yeah, the Earth wobbles on its axis, actually. That's an interesting comment, actually. Just as an aside, Mars also wobbles on its axis somewhat more than the Earth does. But we do have a moon. We have a rather large moon, which stops it wobbling as much as it should. So that actually does help to make it because the variation of the seasons is not as extreme as, say, on Mars over several thousands of years. So thanks for that. That's good comment. One more. Can you think of one more thing?
The amount of water there is in the seas.
Yeah, the amount of water there is. Yeah, that does help. Definitely for life, and it does help stabilize the climate as well. So yeah, water is an important part of why the Earth is a good place for life to be. And all around the system and around planets around other stars to discover where life might be is geared upon looking for the signature of water. So water is quite important. Well, they're all good answers, and all of those contribute to why the Earth is a perfect planet for life. Often when people talk about why is the Earth habitable, why is it a good planet for life, people, as somebody has said, comment that it's far not too close. I'm going to have to it keeps freezing my PowerPoint, so I'm just going to try and get it working again. Right, let's go back. Right, so the Earth exists in what is often called a Goldilocks zone. Yeah.
I wonder whether, I mean, do you have any other computers in your room? Is your phone on? Because I'm getting quite intermittent sound. If you could close down anything else, that might help.
I can close down my phone, but that normally doesn't interfere with anything. There's no other computers in my room.
Okay.
So do that and see if it helps. Okay. So when people often talk about why the Earth is a good place for life, they talk about it being in the Goldilocks zone. What it means by that, it's not too hot and it's not too cold. It exists in this zone in the solar system where water can exist as a liquid, a gas, and a solid all together. Any closer towards the sun, and water kind of boils off into the atmosphere and way into space. Water tends to freeze, and it's difficult to have liquid water. So the Earth is in this kind of special place in the solar system. Venus is just inside of what we call the Goldilocks zone. and Mars is just beyond the outer edge of it. And they're very different planets to the Earth. Actually, Venus is about the same size as the Earth, and actually has a much thicker atmosphere than our planet, comprised mainly of carbon dioxide and nitrogen, than the Earth, and is further away. Because it's small, it's struggled to maintain its atmosphere over the long history of the solar system. It's quite thin now, and it's very cold. Although there are Earth-like features in it, you can see at the poles there are ice caps there, but they're not. That's not water ice. Most of that ice is carbon dioxide. It freezes out the atmosphere in the winter season. The Earth. I never tire of looking at these pictures of the Earth from. And it's a beautiful view. Let me show you a bigger view of it, because you might be able to just about see on that small image something that's really important for why the Earth is such a perfect planet for life. If you look around the edge of that picture, you will see a thin blue line. And that thin blue line is the atmosphere. And we live at the bottom of the atmosphere. It's well, it doesn't really have anything. It just kind of fades out into space. Even 700 kilometers up, there is still some of the atmosphere. But we live at the bottom of it on the surface. And that is an atmosphere composed of various gases. 78% of it is nitrogen. 21% of it is oxygen. 1% of it is water vapor. Most of the water on the Earth is in the oceans, but 1% of it is in the atmosphere. And about 0.03%, such as methane and argon and helium. Thinking about the atmosphere, well, it's this atmosphere actually that makes the Earth suitable for life. Not only is the Earth at the right distance away from the sun, receives a reasonable amount of energy, but the atmosphere actually plays a huge part in warming the Earth, and its response effect. Now, here's a couple of questions for you, and see what you've picked up from your general discussions about the environment. Is the greenhouse effect good or bad for the planet Earth? And what do you think the most important greenhouse gas is? Is the greenhouse effect good for the Earth? And what do you think the most important greenhouse gas is? Any suggestions? If you have suggestions, just unmute yourself. It's bad. Why do you think it's bad?
Because the heat that is trapped inside the greenhouse makes the Earth heat up, and in heating up, more of it becomes uninhabitable, and various systems start to break down.
Okay, so it's bad. Any other thoughts? Is it good or bad?
Yeah, it's bad because it's necessary for humans to exist, and because of humans, most of the bad things that happen are happening.
Okay. Any other thoughts?
I'm going to go for it's good, because if it was not for that, the Earth would really be too cold to be habitable. And I'm also going to make a pitch for water being the most important greenhouse gas.
Okay. Any other thoughts? Either question. You're not going to be marked on this, and I'm not going to give a report on any of the answers. So, you know, just chip in. We're trying to learn together.
I think I'd say it's both good and bad. The greenhouse effect is, you know.
Collins. Good. Go on then. Explain that one.
Well, How can I explain it? Yeah, it's an inevitable part of having an atmosphere, because actually when the sun's rays hit the earth, they will warm the atmosphere. But the question is, how much does it then rebound back in again once it tries to get back out? So it's we need a greenhouse effect in order to keep the earth at a certain temperature, so it's not, like Simon was saying, not too cold.
Okay, thank you. Any other suggestions over what the most important greenhouse gas is? Simon thinks it's water. What about everybody else?
Well, if the greenhouse effect is essentially good, but we're having too much of a good thing, methane is perhaps one of the worst culprits for contributing to the negative greenhouse effect.
Right. Any other suggestions?
I might make a pitch for oxygen, seeing as I think that's what we like to breathe.
Okay. All right. So let's move on from this then. Is the greenhouse effect good or bad? Actually, it's good overall, because it says it exists. It makes the earth warm enough for water to exist as ice, liquid, and gas. And here we go again. If the earth had no atmosphere at all, then its average temperature would be minus 18 degrees centigrade. And all the water that's in the oceans would just be frozen solid. Because we have that thin layer of air around the earth, the average temperature of the earth is 14 degrees. So that's about, I think that's a 30 degrees warming of the earth just due to that thin layer of gas. So what we call the natural greenhouse effect is essential for making the earth a place that's warm enough for life like us to exist. So I think it's, you know, if you want to think theologically about this, it's a gift. It's part of God's gift to us to make a home for us that is habitable and will sustain life for us. And what causes the greenhouse effect? You need to think about how the different gases in the atmosphere interact with two forms of light. Visible light, which is the light that we see by the light that we get from the sun, and what radiation or infrared radiation, infrared light, which is heat, the kind of radiation you will feel if you put your hand next to a radiator and you'll feel the heat coming off it. This is a form of light that you can't see, although we now have infrared cameras which could see, and maybe you've seen those pictures taken of houses with infrared. I want to think about how the gases interact with these two forms of radiation. Firstly, nitrogen and oxygen. Nitrogen and oxygen make the bulk of our atmosphere, and yet they are what we call transparent to both the visible light from the sun and the heat radiation, the infrared radiation that comes up from the earth. So the sun, the earth receives light from the sun, it warms the surface and the ocean of the earth up. The earth emits that infrared radiation. In fact, as far as nitrogen and oxygen are concerned, they're not interested. Oxygen and nitrogen don't absorb or retain any of that energy. However, water vapor and carbon dioxide are different. Water vapor and carbon dioxide, like oxygen and nitrogen, are transparent to visible light. So visible light from the sun comes through the atmosphere and warms the surface of the planet. But water and carbon dioxide trap some of the infrared radiation which is coming back off the Earth that's trying to escape into space. That radiation, it interacts with them to start spinning what we call a rotational vibrational mode. And that traps that energy. And then when it's released, some of it goes back into space and some of it gets pushed down towards the Earth. which warms the planet. Now, if the Earth had no water vapor or carbon dioxide in the atmosphere, then it will be back at minus 18 degrees centigrade. So just that little bit of water vapor and that little bit of carbon dioxide, plus some other gases like methane that has been mentioned, just that little bit of them is so vital for the Earth to be a place where life like ours can be sustained. This is a greenhouse effect. It's a good thing. We call it a greenhouse effect because it's energy. It's a metaphor. It's a bit like the glass in a greenhouse. Vapor and let sunlight in, but trap the heat energy going out. Or actually, the physics of that is rather just that the hot to push the hot air upwards. It traps them in the greenhouse. I think it's more like the duvet effect because I don't know if you have those duvets where there are two layers, and in the summer you take the top layer off so you don't get too hot, and in the winter you put the top layer back on so you warm up. I think the water vapor and carbon dioxide are a bit like a duvet that is wrapped around the Earth, trapping heat in. Now, water vapor play in the greenhouse effect. About half of that 32 degrees warming is down to water vapor. So water vapor is the most important greenhouse gas. Another 25% of that warming is caused by clouds, liquid water droplets in the atmosphere, which also trap heat. About 20% of it is due to carbon dioxide. And then other gases such as methane, ozone and CFCs, they account for about 5% of the warming. As commented, actually, methane is a quite powerful greenhouse gas, somewhat more powerful than carbon dioxide and water vapor. However, there's not much of it in the atmosphere, and it doesn't hang around very long once it's there because it reacts with water to produce a chemical which is lost to space. So water vapor is the most important greenhouse gas. Carbon dioxide is about a fifth of the warming effect. But actually, over the last couple of centuries, the amount of CO2 in the atmosphere go from measurements that we can take of air trapped in sea ice, on ice in Antarctica, land ice, that for much of the last 1,000 years, the amount of carbon dioxide in the atmosphere was fairly static, about 280 parts per billion. But from the late 1700s, onwards, when we started to burn more fossil fuels, first coal, then oil and gas, the amount of CO2 in the atmosphere has risen. Despite the lockdown over COVID was reducing the amount of CO2 that we were producing, it's continued to rise through 2020 and into 2021. We passed in 2020 the mark where there is 50% more carbon dioxide in the atmosphere than there was in 1800. And at the moment, we've reached a level of 417 parts per million. And by adding more carbon, and so the temperature of the Earth starts to rise. Now, there are natural variations in carbon dioxide content of the atmosphere, and lots of different processes affect the CO2 levels. The plant ecosystem, both on land and in the ocean, the algae in the ocean, all withdraw carbon dioxide from the atmosphere. And in fact, a large proportion of the carbon dioxide that humans produce is still absorbed by the ocean. However, if oceans warm, they start to release carbon dioxide back into the atmosphere. But some carbon dioxide is taken out of the atmosphere by the weathering of rocks, and volcanoes both, they release carbon dioxide into the atmosphere that's stored deep in the earth, but the movement to the surface tectonic plates tends to bury carbon dioxide as well into in the stabilization of carbon dioxide in the atmosphere on very long timescales of thousands of years. Now, scientists have estimated that in the past, the Earth had a lot more carbon dioxide in the atmosphere. About between 50 and 30 million years ago, there was probably about 4 to 5 times the amount of carbon dioxide in the atmosphere than we have. This was a much warmer world than the one we live in now, a greenhouse world, where there were only very, very small ice sheets at the pole. But gradually, over time, some of those geological processes drew down carbon dioxide in the atmosphere to levels which are similar to ours today. And for the last 20 or 30 million years, we have had carbon dioxide at a relatively low level in the atmosphere, which we observed 200 years ago. A good idea of what's been happening in the last million years of the history of the Earth by looking at these ice cores in Antarctica. People drill down into the ice and take an ice core out of the Antarctic ice sheet. And inside the ice cores are bubbles of air, and they can be sampled. And two things you can find out from them. One is how much carbon dioxide was in the atmosphere. And you can actually get an estimate of the temperature of the planet by looking at two versions of oxygen. Oxygen, which is of oxygen you find in the atmosphere, and another form of oxygen called oxygen 18 has a different number of neutrons in its nucleus. What we can find from this is that actually over the last million years, the temperature of the planet has gone up and down as the ice sheets over the poles have expanded southwards from time to time. This is primarily driven by the wobble in the Earth's orbit around the sun, the wobble of the Earth on its axis, and the way the distance of the Earth as it goes around the sun. And you get periods when the Earth is very warm, like today. We're in an interglacial period at the moment. And you also get phases when the Earth is very cold, when, for example, most of England and Northern Europe is covered in an ice sheet, as is Canada and parts of North America. What the measurements of the Antarctic ice sheets have found is that when the Earth is warm, there is more carbon dioxide in the atmosphere. And the Earth is cold, carbon dioxide in the atmosphere. We had a few more lines on here to show you some of the level of carbon dioxide that there is. The bottom graph there is carbon dioxide. The top graph there is temperature of the Earth. And you see there's a correlation between temperature and carbon dioxide. Now, Al Gore, in his film An Inconvenient Truth, which is a great film, and really, you know, he was trying to alert people to the dangers of climate change almost years ago. He stood in front of a picture like this and said, there you go. The more carbon dioxide in the atmosphere, the warmer it is, the less carbon dioxide, the colder it is. In a great film, that mistook a correlation for cause. One thing that scientists, it's rammed into scientists when they do research, is correlation is not the same as cause. And actually, the cause of the ice ages is not the variation of CO2 in the atmosphere. As I said, the cause of ages is because of its axis, and its distance from the sun varies slightly, and that causes it to receive less or more energy from the sun. So what's happening in an ice age cycle is that because the Earth's orbit wobbles, we receive less heat from the sun. And when we receive less heat from the sun, that triggers the planet, the Earth, to cool. And as the Earth cools, then ice increases over the sun. But that also reflects more sunlight back into space. So the Earth then receives less energy, and it causes a further temperature decrease. At the same time, there's a natural decrease in CO2 in the atmosphere. Not all of this is understood. Some of it is down to the biology of the oceans, that colder oceans actually enable some of the plant life to flourish. I remember being in a talk by James, actually, the ice age climate was quite good for life, to which one of the scientists at the Met Office said it didn't seem very good for humans. James Lovelock replied, yes, but it was great for the algae and the plankton. So there are processes in the natural world which actually on a colder Earth draw CO2 out of the atmosphere. And because there's less CO2 in the atmosphere, then the planet cools further, leading to an intensification of the ice age. These secondary loops are called feedback mechanisms, and they amplify the effect of the difference of the radiation the Earth is receiving from the sun. Now, compared to what is happening in an ice age, where the changes can take 5 to 10,000 years to go between a cold and a warm phase, what we have been doing is like giving it a big kick. In a very, very short amount of time, less than 200 years, we have increased the amount of carbon dioxide in the atmosphere from 280, well, it's 419 is the current level. And if we carry on burning fossil fuels in the way that we have been doing through the 20th century, by 2100, the end of this century, the amount of CO2 in the atmosphere will reach 680 parts per million. That's more than double the amount it has been for the last 500,000 years. And we're doing it on a very, very rapid timescale. So it's no wonder that the Earth is struggling to adapt and cope. When CO2 increases, usually over geological timescales, there are mechanisms which act to draw it down. But when it increases rapidly, such as we are doing now, it struggles to draw it down. It just doesn't have the mechanisms that can respond. So in the situation we find ourselves now, the radiation coming from the sun is relatively constant, but we're increasing the amount of carbon dioxide in the atmosphere. What happens then is that triggers temperature increases as some of the feedback mechanisms kick in. So we get one feedback mechanism, which means a warmer planet. There's less ice at the poles, and there sunlight is absorbed, especially over the North Pole. You might have seen stories about the concerns over reducing sea ice over the North Pole and the rapid temperature rises that are occurring there. And then a warm atmosphere can actually hold more water vapor. So as the atmosphere warms, more water evaporates from the oceans and the land and ends up in the atmosphere, increasing the water vapor. And that adds to the greenhouse effect due to the increase in carbon dioxide. Also, you might get more clouds. About whether the increase in clouds will warm or cool the planet. That's still a topic of research. There's also the other possibility that a warmer planet might trigger the release of some of the greenhouse gases that are stored in the Earth. Over the Northern Hemisphere, in what we call the permafrost regions, there's a huge amount of carbon dioxide and methane stored, frozen in the ground, in the water. And there are, as the permafrost melts, this will release a lot of methane into the atmosphere. There are also methane deposits deep in the bottom of the ocean. And again, as the oceans warm, there's worry that methane will be released from them, which again will increase the temperature of the planet. This is just a graph showing you how the temperature of the Earth has varied over the last 1,000 years. We have proxy measurements. We don't have thermometers measuring temperature over the last 1,000 years. over about the last 350 years. But there are things like tree rings and sediments at the ocean, bottom of the ocean, which actually give us a measure of the temperature of the planet. And although there have been ups and downs in the temperature, on the whole, it's been relatively stable, with a slight decrease in temperature actually over those 1,000 years. But you'll see over the last part of that, on the last 150 years, this started to be a rapid increase in temperature. And scientists think this is driven by these increases of carbon dioxide in the atmosphere. This is the latest picture of a graph that you might have seen in different form, but it just shows you year by year the temperature of the planet compared to an average between 1850 and 200, I think. Might be slightly slower period than this. But actually, over the last year, they warmed up and down from year to year. That's to be expected. There's always variability in the weather. But overall, the average temperature of the planet has warmed. And the last 10 years has been the warmest decade on record. Now, as I said earlier on, I was involved in building climate models. We can use climate models to investigate how the increase of carbon dioxide in the atmosphere will lead. But we can also use them to investigate how the temperature of the planet has varied in the past. A climate model is a very sophisticated computer program which attempts to include all the processes by which the weather and the climate of the planet is changed. So we have in things like we have a land and we have an ocean, and in some of the current and latest models we have representations of plants, how they react to carbon dioxide and energy from the sun. We have exchanges of heat between the land and the sea and the ocean. We have clouds and wind, how the air is moved around. We have representations of the incoming energy from the sun and the energy that is emitted by the earth. And we even have things these days such as dust in the atmosphere, both from natural sources and the pollution that we put in the atmosphere from our industries. And this is what we use to try and predict what's a century due to increasing CO2. But then we can look at the past as well and try and see how, well, what is responsible for the warming of the Earth that we've seen through the 20th century. And we can consider both natural and man-made effects. So we can consider things like the growth of carbon dioxide in the atmosphere due to the burning of fossil fuels. We can consider the pollution that we put in the atmosphere, which acts to reflect some of the solar radiation back into space. And we can think about some of the natural sources of carbon dioxide, such as volcanoes, and also variations in energy from the sun. And we can put all those factors into one of our climate models. And we can run the model to try and see if we can predict the temperature of the Earth as it's varied through the 20th century. This was work that was done in the late 90s at the Hadley Centre at the Met Office. Climate models are natural variations that we see over the last 100 years, such as the way the energy from the sun has varied slightly, or the volcanoes that erupt and put lots of aerosol high into the atmosphere, which shield the planet, or the way the ocean temperature varies from year to year, then this is what we find. The black curve there is the observed temperature of the Earth from 1900 onwards to the end of the 20th century. The blue curve is the period predicted by the climate model. Now, models are never perfect. There are always things we don't understand, and there are a lot of things we don't understand about the processes in the atmosphere, especially around the area of clouds, which is what I used to work on. However, by looking at the natural forces only, what we don't see coming out of the climate model is this increase in temperature through the latter part of the 20th century. Through the early and mid part of the 20th century, was the observed and the model temperatures are in the same kind of ballpark. But we don't see this warming trend in the latter part of the 20th century. In fact, the model suggests that the Earth should have cooled slightly through that period. If we then put in the impact of increasing carbon dioxide and also industrial pollution in the model and run the experiment again, then this is the curve that we find. Again, agreement is not perfect, but what we do see is in the latter part of the Earth in the model begins to match the temperature of the Earth that we see in the observations. By the way, we don't just run the climate model once for this. We run lots and lots of different simulations of the climate of the Earth with slightly different parameters and different starting conditions. And so the red and the blue curves are averages over lots of runs, about 30 runs of the climate model, to give some idea of what variation might do. So far, observations tell us that we have warmed the Earth by 1 degree by putting more carbon dioxide in the atmosphere and the feedback mechanisms that we see. If we carry on emitting carbon dioxide in the way we have been doing, then the planet by the end of the century will potentially warm by 5 degrees. Now, attempts are being made, and there's another UN climate conference this year to make further agreements to try and limit the amount of carbon dioxide. So we zero emitting carbon dioxide by 2050. At the moment, the pledges that various countries, including our own, around the world have made to that aim, that's going to limit the warming to 3 degrees by the end of the century. The latest IPCC report advised that we should try and limit the warming to 2 degrees, although 1.5 degrees will be better, because some of the extreme effects of climate change won't be as bad. You need to understand, though, even if we stop tomorrow and we didn't increase the amount in the atmosphere at all, we are still committed to more warming, probably up to 1.5 degrees, because there are lags in the system. And there is still extra energy that the carbon dioxide we've already put into the atmosphere hasn't yet trapped. This is a picture of the temperature of the Earth in 2019. You know, already that warmer than the previous average baseline temperature that we observed over the past period of human history. The greatest warming is at the poles, where we're seeing warmings of 2 degrees at the North Pole. And increasingly in summer, there is less and less sea ice over the North Pole. If we run the climate models forwards with increasing amounts of CO2 in them, then this is what the temperature of the planet will look like at 2100. 2090. The poles are still the warmest, this time by 9 to 11 degrees. The land areas have consistently warmed between 5 and 9 degrees. Here in the United Kingdom, because we're next to an ocean and it takes longer for the oceans to respond, actually there's some mitigation of the effect, but still in our average temperature will warm by 3 or 4 degrees. So this is the world that our grandchildren and great-grandchildren will find them in, and they're starting CO2 that we're pumping into the atmosphere. I'm going to kind of leave it there for the science, and maybe you've got some questions to ask about what I've said. I hope that was understandable. But here are just some questions I thought you might like to ponder tonight. God said that it was good when he looked at the earth that he had made. I wonder what that means for you. Was it perfect? Or is it good enough? Good enough for purposes be achieved. I wonder what that phrase, God saw that it was good, says to you. And I just wonder, how does your understanding of the science of global warming increase our appreciation of God? Enable us to wonder more, respond in wonder to the world that God has gifted to it. Does it help us to understand the connections that we have with the rest of creation, or God's purpose that he has for our planet and for us? What do you think our response is to control CO2 emissions? And who's that responsibility to? Is it to God? Is it to people in the current generation or future generations? Or is it to the entire community of creation? Because we are not the only ones who are impacted by climate change. So just a few questions perhaps to ponder in our discussion, along with any questions that you have. I will stop sharing the screen now so we can see one another. Okay, over to you. Any questions?
Well, Dave, just before we go to our questions, just want to say a really big thank you to you. I found that absolutely fascinating, and certainly I felt it helped my understanding a lot. So thank you so much.
Thank you. There we go.
So let's have some questions.
I'll throw a question at Dave, if that's okay.
Yeah, Michael.
You talked a little bit, a tiny bit about the negative feedback loops when you go into colder climates.
Yeah.
That just made me think, is there anything in climate models that, like, if we start doing this, that might feed into negative feedback, like good decisions we make now that might speed up cooling?
Yeah, I mean, there are negative feedbacks in the system. So trees, forests, the way we use land, that can be a negative feedback. I mean, trees are a natural sink of CO2, which takes CO2 out of the atmosphere. I mean, in fact, the dust and the industrial pollution that we put into the atmosphere, which tends to go with the CO2 we produce, or it used to, actually that produces a cooling effect on the planet. And one of the reasons why we probably didn't see warming through the 50s into the 60s is that our industry was very dirty. And that kind of acts like a reflective shield, the dust. If you've seen some of the pictures of China, Beijing on a bad day, with that yellow orange smog, that's the result of that aerosol pollution, little particles we put in the atmosphere. Of course, we've cleaned up our industry to a great extent, so that feedback has been taken out the systems, and it does anything. You wouldn't put it back in the system. And our climate models actually would take account of those kind of the feedbacks. So one of the important things about them is that you want them to capture some of the positive and the negative feedbacks correctly, so we get a good estimate of the potential of the warming of the planet. And also to investigate, are there any mitigation effects that we might want to do? So some people have suggested that we, rather than control CO2, that we push up dust particles into the stratosphere to act like a sunscreen for the Earth. Now, I think that's dangerous because we don't fully understand the consequences of our actions when it comes to the atmosphere. It's a very unstable, what we call a chaotic system. Small changes have huge effect. We talk about the butterfly effect in meteorology. The flap of a butterfly's wing over the Amazon causes a tornado 5 days later in Texas. Well, that's a bit of hyperbole, but there is truth in it. Little changes can have big effects, and things that to produce negative feedbacks that we could try engineering wise. We just don't know what the consequences would be, potentially.
Dave, I'm stretching my abilities to get the right terminology here, so I'm sorry. This is Mark.
Yeah, hi, Mark.
I think you said that the current plans are to reduce the warming to 3 degrees.
Yeah.
Is it possible, is it feasible, if the will was there, to reverse the heat, the warming completely?
No, sadly not. Not in kind of human timescales. So, you might have heard it said that the Paris Climate Agreement has kind of set a target that we would stop emitting CO2 by 2050. That will be net zero carbon dioxide emissions by 2050. If we did that, then the science says we'd be limiting the warming to 2 degrees. The agreement actually says they would try to limit it to 1.5 degrees, but to do that, we in the latter part of the 21st century. Now, we just don't know how to do that. We don't know how to do it on an industrial scale to make a difference at the moment. So we're not going to, it's going to be very difficult to reverse the warming, and it will probably take a couple of centuries or longer if we were able to remove the excess CO2 from the atmosphere. I mean, planting trees would be a good way of mitigating some of the effect, but we're not going to be able to get rid of all the effect. And in fact, although we talk about 21 warming actually for another couple of 100 years until it reaches some kind of equilibrium. So we're not done with the warming at 2 degrees even if we reach net zero at 2050. The planet is going to warm for the next couple of 100 years after that.
Yeah, thank you.
Thanks. Yes.
Okay, so with these rockets, spaceships going up through the atmosphere, and with this butterfly effect, is that making any effect?
That question a long time ago at a bus stop in Nottingham. It was a Friday night, and to be honest, I was on the way to the pub. And if you come from Nottinghamshire, you stand at a bus stop, people will talk to you, unlike down in Croxley Green. And an old lady was at the bus stop. We'd had terrible weather at that time. We were talking about the weather, and she said to me, "I blame the Russians putting their rockets up into space. That's what's causing it." No, we launched so few rockets, it has very little impact. And some of the rockets burn oxygen and hydrogen just because they use kerosene, and they produce a lot of dirty dust as well. You might see an orange trail behind a lot of the rocket launchers, but really they're too small to have much impact upon the climate of the planet. But you're not the only person to ask that question, so don't you? No.
Can I just ask, in a similar vein? Sorry.
Yeah.
Can I just ask, in a similar vein, air travel?
Yeah.
Is that? Would you say that is a major contributor? Is that something that should be drastically looked into in the future, in terms of finding different means of fueling aircraft, or just that we should stop flying around the world? What are your thoughts on that one?
I mean, that's the one that is often brought up in terms of how we're going to reduce our carbon dioxide emissions. We should stop flying. Flying does increase CO2 emissions, and the growth in flying over the last 20 or 30 years has certainly seen a rise in emissions due to air travel. And there's some thought that because they fly so high, the carbon dioxide they put in the atmosphere might have a stronger effect. But actually, most of the CO2 in the atmosphere arises from our production of energy on the ground, electricity, and actually driving our cars and vehicles on the ground. So really, I think that the main things that we need to do to make a difference at the moment is think about how we generate electricity. Switching to renewables. We actually have done a good job in the UK, and other countries have around the world. We've stopped using coal. I mean, there have been phases in the last couple of years when we've burnt no coal at all to generate electricity. And this is good because coal produces a lot of carbon dioxide. What we've done to replace it, though, is switch to gas. Now, gas produces less carbon dioxide, so it's a win, but it's still producing carbon dioxide. And looking ahead, the hard journey we are going to have to go on in the next 10 to 15 years is stopping using gas and switching to renewables. Now, actually, I'm amazed at how much renewable energy we now have on tap in this country. Sometimes it's 30% of our electricity supply is produced by renewable energy, which is an amazing journey. But the hard thing is going to be, how do we get off gas? And I think that probably ought to be a focus rather than purely the focus being on how do we stop flying. However, I think it would be right for us to try and cap the level of flying that we're doing. And you know, government policy is still looking to make more flights in. Now, to me, that is nonsensical when actually we've committed ourselves as a country to reduce our CO2 emissions by 68% by 2030, which is a really ambitious target and a good thing. But at the same time, we're talking about ramping up some emissions as well as developing a new coal mine. May not be sensible.
Right. I'm going to disappoint people, but I'm going to call our questions to a close. I think we could probably go on asking you questions all night, Dave, because you know we're really interested in this subject. But you may remember that a while back I asked if people would like to contribute some or tell us about what they are doing personally in relation to some action in regard to the environment or climate change or so on. So, and Mike has kindly offered to say something about what he's doing. So I'll hand over to you, Michael.
Hi, yeah. Shane, when Mark says everyone would like to talk, I was like, yes. Actually,
If you can speak up a little bit or be a bit closer to your microphone.
Yeah, sorry, I always mumble on this microphone. Is that better?
Yeah, a little bit.
A little bit. Okay. Oh, wait. By the computer microphone. Hopefully that will be a bit better. So yeah, I was really keen to jump on this because don't think I've mentioned, but I am part of something called Young Christian Climate Network, or YCCN, and we are organising a event this year to go from a G7 leaders summit in Cornwall to something that Dave mentioned briefly, which is the UN's climate summit in Glasgow. So these are two huge political events that are happening in the UK this year, and we are going to be doing a relay in between them. So we're going to be walking on foot from Cornwall to Glasgow, different people joining in at different times, and yeah, hopefully it's loads of fun. We're going to have a load of media and a few demands, and we're going to be raising issues mainly around climate finance. So how the countries that might be hit worse from some of these effects that happen due to global warming, how those countries finance their relief, and making sure we're not pushing these people further into debt through actions that are completely out of their control, is going to be our main ask. To be like at COP26, you need to be talking about climate finance. So yeah, we're organising, we're happening. We're going to be walking all the way through the UK. And my shameless plug is, you know, if you're on a route somewhere between Cornwall and Glasgow, which you might be, and you're interested and want to get involved, you can either grab my email off Simon, or you can go to yccn.uk, which will be our website, and you can sign up for newsletters, eventually newsletters. We are early days. But yeah, we should have loads of news. Yeah.
That sounds like a great initiative, Mike. And can I ask, do you have a particular role in organising it?
I am route planner, is my hat that I'm wearing at the minute. so we've got a little core team of about 8 of us, and I am sorting out routes, and I'm going to be route coordinating for the south in the end. So yeah.
Excellent. And the dates?
So G7, which is mainly around Europe, is at the end of June. So we'll be around Carbis Bay in the 26th of June, and COP26 starts in Glasgow on the 1st of November. So we will be arriving in Scotland at the end of October. Will be when we're in the north.
Sounds like a brilliant thing. Okay, well, you know, anything you want to shoot in my direction, I'll circulate it to everyone. Yeah.
Thank you very much.
Can I just comment that hopefully with Bwen we're going to kind of encourage Baptist churches to engage with that journey to COP that YCCN are doing. It's a really good initiative. And that new network, Young Christian Climate Network, which is great to see. So thanks for that, Michael. Sounds really good.
Thanks, Dave. Yeah, great talk tonight as well. Thank you for that.
Thank you.
Well, Dave, if it's okay, I'll say a short prayer just to close our time together. Okay?
Great, thanks, Simon.
Yeah, Heavenly Father, you know the things we've been looking at and thinking about, and I think it's just really helped us to grasp what a wonderful and extraordinary world that you've placed us on, with so many things being really finely balanced, made perfect for life to exist here. And we're so sorry that through our actions, through our ignorance, that we are upsetting that fine balance. And just to pray that you will help us to be conscious, to be aware of what is going on, what the outlook is, and therefore to understand what we individually, collectively need to do. And we also thank you for Mike and the initiative that he and YCCN are taking, and pray that you'll bless that initiative, and pray that that will also contribute to raising awareness within us, within the nation, but also, of course, within the church, and that we as a church will be playing our part and taking lots of initiative. So we pray these things in your name, Lord. Amen.
Amen.
Well, thank you once again. Really appreciate that. Yeah, I'm glad that you got a lecture from someone who knows what they're talking about. I'm afraid the group tomorrow will not be quite so fortunate, but
a little bit.
Yeah.
Yeah, sorry I can't come back tomorrow. I have to go and look at a house.
No, it's really good. Okay. Well, I should
Thank
say
you.
goodbye. And if you can remember, our next lesson will be 3 weeks from now. Okay. Good. Thank you.
Thank you.
All right.
Simon.
Good night, all.
Thanks very much. Thank you.
Very much. Thank you. Bye.
Thanks, Simon. Thanks, Dave.
Bye, everybody.
Bye. Bye, Elaine. Bye, Christine. Bye, Colin.